Triangle trap air, fuel, spark. Density determines the mark. You know, if you spend your days designing, inspecting, or operating industrial facilities, you already know that the physics of an explosion rely entirely on bringing those three elements together in the perfect, disastrous ratio. But in hazardous area engineering, our job isn't just knowing the triangle, it's meticulously dismantling it, piece by piece, using some very strict mathematical thresholds.
Welcome to this explainer. Think of today's session as your absolute ultimate survival cheat sheet for industrial safety standards. We're pulling directly from the foundational codes, specifically the IEC 60079 series, API, and ATEX directives, to distill the exact formulas and key figures you need. No fluff, just the raw data and criteria used to keep explosive atmospheres safe.
Okay, let's set up our mental filing cabinet for the 5 plays we'll cover today. First, defining the explosive hazard. Second, mapping zones and ventilation. Third, gas groups and temp classes. Fourth, protection types. And finally, verifying intrinsic safety.
Starting with number 1, defining the explosive hazard. Every great safety protocol has to begin by understanding the fuel side of the fire triangle. Before we can actually protect a space, we have to know exactly how much gas or vapor it takes to cross the line from a harmless little leak into a full-blown explosive threat.
And that brings us to the explosive range. You'll use this concept constantly when assessing whether a specific gas concentration can actually ignite out in the field. Below the lower explosive limit, or LEL, the mixture is just too lean, there literally isn't enough fuel. Above the upper explosive limit, the UEL, it's way too rich, meaning there isn't enough oxygen. The real danger zone is strictly between these two numbers. If your facility's gas concentration hits that sweet spot and a spark occurs, well, you have an explosion. Moving right along to Section 2, mapping zones and ventilation. Once we understand the fuel itself, we've got to map out the physical spaces where these hazards might pop up. After all, we can't treat a pipe flange that might leak once a decade the same way we treat the inside of a continuously venting storage tank, right? We handle this by assigning grades of release, which translate directly into zone classifications. A continuous grade of release, where the hazard is just always present, gives you a Zone 0. A primary grade, which happens during normal, everyday operation, gives you a Zone 1. And a secondary grade, which is an accidental or super rare leak, dictates a Zone 2. You use these rules of thumb to immediately scale your equipment requirements based purely on the statistical frequency of a hazard.
Now, when you need to translate overlapping international standards for a globally sourced facility, the direct equivalents are a lifesaver. IEC Zone 0 is equivalent to API Division 1, which perfectly equals ATEX Category 1G. Zone 1 also maps to Division 1, but it drops to ATEX Category 2G. And finally, Zone 2 aligns with Division 2 and ATEX Category 3G. Having this conversion firmly locked in your head will honestly save you countless hours during equipment procurement.
But here's a really cool twist. Ventilation can actually shrink those zones. Engineers use these exact figures to prove an area is safe. If you have natural wind speeds of 0.5 meters per second or greater, you achieve rapid dilution. If you're indoors, you calculate VZ, the hypothetical dilution volume, and T, the persistence time. If those numbers come out too high, you have to size mechanical fans to dilute the gas. Doing that can effectively reduce a Zone 1 area down to a Zone 2, or hey, even make it unclassified entirely.
All right, let's transition to Section 3, gas groups and temp classes. We are zooming in on the specific chemical properties of our hazards here, because it's not just about how much gas is present, but exactly how easily that specific gas ignites, both by a spark and by sheer heat. Before we dive into the data, I want you to remember this classic field mnemonic. IC is critical, T6 is cool. Reverse the logic, know the rule. Equipment ratings can feel super counterintuitive, where a higher letter actually means a more dangerous gas, but a higher number means a cooler, safer piece of equipment. Let's break that down a bit.
You absolutely must use these classifications when selecting the gas group rating for your electrical equipment. Group IA gases, like propane, represent a lower risk because they require a bit more energy to ignite. But Group IC gases, like hydrogen, highest risk. They take incredibly minute amounts of spark energy to go boom. If your equipment is rated for IC, it's robust enough to handle IIB and IIA, but never the other way around.
So the crucial point here is matching your equipment's surface temperature to the gas's auto-ignition temperature. T1 allows a surface up to 450 degrees Celsius, which is really only safe for hard-to-ignite gases. But a T6 rating means the equipment's surface maxes out at a very cool 85 degrees Celsius, making it perfectly safe for all gases. Also, quick pro tip, if a nameplate doesn't list an ambient temperature range, standard practice dictates you assume a default of -20 to +40 degrees Celsius when verifying it for your site.
Moving right into Section 4, Protection, Types, and Clearances. We're shifting focus to the physical defenses. How do we actually construct our electrical circuits to defend against the spark and heat sides of the fire triangle?
A handy way to lock in the primary protection concepts on the fly is this quick rhyme. Ease it durable, cools the flame, saves the game. Ease for extra care, no sparks in there. Exit is flameproof. It literally allows an internal explosion, but cools the escaping gases so they can't ignite the outside world. XE is increased safety. It's built so robustly that arcs, sparks, and hot surfaces are prevented from ever occurring in the first place.
And inspectors use this exact matrix when auditing XD enclosures. The gap between a flameproof joint and any solid obstacle must be strictly maintained to allow escaping gases to cool down. For IIA gases, you need a 10 mm clearance. For IIB, it's 30 mm. For IIC, it's 40 mm. On top of that, when selecting cable glands for Zone 1, you must use a compound-filled barrier gland unless the gas is not IIC and the enclosure volume is less than 2 cubic decimeters.
Now, for XE increased safety motors, you really need to know the TE time. This is the locked rotor overheat time. Literally, the exact amount of time it takes for the motor rotor or stator to reach its maximum safe temperature if it stalls while running. You strictly use this figure when setting the overload relay curves. That relay has to trip the power before the TE time is reached, otherwise your safe motor becomes a lethal ignition source.
Finally, we reach Section 5, Verifying Intrinsic Safety Loops. If XD contains the blast and XE prevents the spark physically, intrinsic safety, or IS, is the ultimate method of starving the spark entirely at the electrical level.
To quote the source material perfectly here, I is impotent, the spark is too weak to bite. Intrinsic safety works by fundamentally limiting the electrical energy, both the voltage and the current, available in a circuit, so that even in a worst-case short circuit, the resulting spark simply does not have enough thermal energy to ignite a gas mixture. It's brilliant!
Designers use these categories to select the proper IS barrier depending on just how deep into a hazardous zone the instrument actually sits. Category IA is safe even with 2 independent faults, allowing it to be used in Zone 0, 1, or 2. Category IB is safe with 1 fault, which makes it suitable for Zones 1 and 2. And Category IC is safe only in normal operation, restricting it strictly to Zone 2. Let's see how this builds into the core verification. If you don't have a prepackaged system certificate, you have to verify the IS loop mathematically yourself. The field device's maximum voltage, current, and power input, UI, II, PI, must be greater than or equal to the barrier's maximum output, UO, IO, PO. Then, you have to ensure that the capacitance and inductance of the cable, plus the internal capacitance and inductance of the device, are less than or equal to what the barrier can safely handle, CO and LO.
But what if you want to use a basic component, like a simple thermocouple or a switch? Well, you use the simple apparatus thresholds. If the device generates or stores less than 1.5 volts, 100 milliamps, and 25 milliwatts, it doesn't even need formal X certification to be used in an IS loop. You just calculate its maximum surface temperature using this straightforward formula. TA equals the barrier's max power output, PO, times the thermal resistance of the device, RTH, plus the ambient temperature, TAMB.
All right, pay close attention to the single, highly scrutinized number, 50 millimeters. When you are laying out a shared control panel or cabinet, you absolutely must maintain an exact physical separation of at least 50 millimeters, or use a grounded metal barrier plate between any intrinsic safety terminals and non-IS terminals. This guarantees that a stray, high-energy wire can never accidentally contact your perfectly balanced IS loop. We've covered a ton of ground today. The explosive range, zone mapping, gas groups, physical clearances, and intrinsic safety loop math. Every figure, every formula we just explored is the literal barrier between safe operations and total disaster. So, I leave you with this. Do your current facility diagrams and field nameplates truly reflect the reality of your hazard triangle, or is it time to take this playbook out into the plant and put it to the test? Thanks for joining me on this explainer, and definitely stay safe out there.